Before you even think about how to prove if an identity is true, try to convince yourself that it's false. And here's one way to do that is by just graphing the thing. Guess I don't need this at this point. I guess I can just do that. No, that was not efficient. Let's just graph both sides of this equation. 1 minus tangent squared x all over, that worked correctly, good, sine x minus sine x times tangent x. There we go. So there's whatever function that is, the left-hand side of that equal sign. On the other hand, tangent of x plus tan. Those two look like they line up pretty good? Yeah. So if they're not exactly equal to each other, they're at least really close. And that's suggestive that probably these two things are actually equal. Let's try to prove. So let's try to use algebra to prove that these two things are actually equal to each other on the nose. And one way to algebraically prove an identity is take the side that's more complicated, and hopefully that'll simplify down to the side that's simpler looking. Is there a side of that equation that's obviously more complicated? Yeah. Let's take that side and see how to simplify it. And there's a description of some steps that might be useful. I guess factoring is something that apparently seems reasonable. Is there factoring you could do to that more complicated side? At the very least, look at the denominator. Everything in the denominator have a common factor? Sine x. Let's try to factor that out. And there's no wrong step to do when you're trying to prove an identity. As long as the step is mathematically correct, it's not wrong. So let's factor out that sine of x. 1 minus tangent x. What about the numerator? Does that factor in any useful way? It's not like there's like a single obvious thing that you could pull out. But let's just look at it this way. This isn't part of the proof. This is part of just motivating what to do. Replace tangent with t just so you don't have to write tangent. 1 minus t squared. Is that a polynomial that you know how to factor? That does a factor. Well, I think that maybe it would be useful to just state the following. So the following is a formula that you should keep in your back pocket. So for any numbers a and b, whenever you see a squared minus b squared, so whenever you see a difference of perfect squares, you can always factor that. A squared minus b squared factors as the difference times the sum. And now that you see it written down, like, it's true, right? You could expand out the right-hand side. So let's use that. So 1 minus t is 1 a perfect square? Yeah, it's the square of itself. So 1 minus t squared is equal to 1 minus t 1 plus t. So that means this numerator factors. It factors as 1 minus tangent x, 1 plus tangent x, and here's the payoff. Does anything cancel? Yeah. There's 1 minus tangent x multiplied in the numerator and multiplied in the denominator. So by canceling, what do you wind up with if you cancel those? How neat. Is that exactly what we wanted to wind up with? So here's the goal if you're following this strategy to prove an identity. Take the more complicated side, and while explaining exactly what's happening in every step, try to reduce it down to the simpler side. So in this case, 1 minus tangent x divided by sine x minus sine x tangent x. By factoring, you get that down to 1 minus tangent x, 1 plus tangent x, all over sine x, 1 minus tangent x. By canceling, and maybe we can even be specific, by canceling the 1 minus tangent x's, you get down to 1 plus tangent x all over sine x. So here's the point that I'm trying to get across. When you write down a well-written proof of an identity or any other mathematical claim, it should be absolutely clear why every step is true, exactly what's going on in every step. So let's carry on. Here's a similar problem. Let's establish that identity. Tangent times cosecant is equal to secant. Is there a single side of that equation that's obviously more complicated looking? Take a look at that more complicated side, and maybe even following the rough outline of steps given there, complete that proof. So let's try to go through it. Tangent, so we want to walk with tangent times cosecant, try to reduce it down to secant. Sometimes it's useful if you don't see any other steps to do. Get things down to just sine and cosine, because then at least there are only two pieces on the board, only sines and only cosines. What do you get if you rewrite that in terms of sines and cosines? Yeah. So apparently there's something that should cancel. What cancels? There's a sine of x in the numerator and in the denominator. Everything's multiplied, so they cancel. All right, so you wind up with just 1 over cosine of x. And what is 1 over cosine x? Secant. Nice. So both of those were fairly straightforward proofs to go through. The point is, you have some identities that you already know how to walk with. You can rewrite any trig functions in terms of sine and cosine. That's something to remember that you have in your pocket. Any other fact that you already know about trig functions is a fact that you can use when you're proving a trigonometric identity. And we'll use one in this next one. In this next exercise, we will prove the following identity, which is sometimes called a Pythagorean identity. Tangent squared of theta plus 1 is always equal to secant squared of theta. And there's stuff on the next page. I'll go over there and do it. So let's try to prove this identity. One side is obviously more complicated than the other. Tangent squared plus 1 is the more complicated looking side. Let's try to reduce that down to secant squared of theta by using stuff that we know. And the first move that I'll suggest is let's rewrite everything in terms of sine and cosine. What's tangent squared in terms of sines and cosines? Sine squared theta over cosine squared theta plus 1. And, well, that looks like a situation where I want to add fractions. 1 is a fraction. It's 1 over 1. So let's get a common denominator. So what do you do to this to get a common denominator to add those fractions? Yeah, you can rewrite that 1 as cosine squared over cosine squared. So this is equal to sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta. Now that we have a common denominator, it's easy to add fractions. So there are like two steps that basically always go in order. Whenever you want to add fractions, you probably need to get a common denominator. And whenever you get a common denominator, you're probably doing it so you can add fractions. So let's add these fractions. Looks like we get sine squared theta plus cosine squared theta all over cosine squared theta. All right, do you see anything useful there? Yeah. Yeah, sine squared plus cosine squared is always 1. And that's because of the Pythagorean identity. So the Pythagorean identity says sine squared plus cosine squared is always 1. So here's the point that this one's trying to get to come across. If there's an identity you already know, you can use that when proving any new identity. We already know the Pythagorean identity is true, so we can use it. And finally, let's wrap this up. What's 1 over cosine squared equal to? Secant squared. Secant because of the 1 over cosine and squared because of the squared. Nice. So, for absolutely any angle theta, tangent squared theta plus 1 is always the exact same as secant squared theta. There's a third identity which is often also called a Pythagorean identity, namely the identity that says that cotangent squared plus 1 is always equal to cosecant squared. I want you to prove this one. I'm going to be quiet for, I don't know, like 5 minutes, maybe less. You'll get an argument, and then we'll try to talk through it. coming from inside the room or outside the room? Outside? Okay, well, I guess there's not much I can do about it other than shut it off. Just wait. Cool. What sort of strategies? Well, let's talk through a proof. So, unless do people want more time before we do that? Okay, let's talk through the proof of this. Cosine squared, cotangent squared plus 1 is apparently the exact same thing as cosecant squared. Why is that true? What strategy did someone follow? Yeah.
I did basically the same thing that we did on the previous cotangent squared plus 1, but with cotangent squared plus 1. So I expressed it in terms of sine and cosine. So we're just doing that up there.
Nice. And what is cotangent in terms of sine and cosine?
Cosine squared over sine squared.
Cool. All right, certainly a reasonable choice. When you don't see anything else obvious to do, it's probably a good idea to get in terms of sine and cosine. What next? Yeah. That's reasonable. Presumably you want to add fractions in a moment too. So let's do those two steps. So getting a common denominator, and I know what the next step is going to be. It's going to be adding fractions. It looks like I'll get cosine squared over sine squared plus sine squared over sine squared, because I want a common denominator, so it better be sine squared. And now you add these fractions. What do you get when you add them up? Nice. All right, what next? Cool. All right. Are we done? Yeah, I mean, basically, but like, not totally done. I need to get cosecant. Cool. People feel pretty good about that? So how many people wrote down the sequence of equations, but maybe, how many people left out all the WODs when they wrote down their argument? Cool. So, especially, well, maybe a good motivator is in the context of the homework associated with today, I absolutely want to see all the WODs. Because the point is you want to have all of the reasons that every one of these steps is true totally explicit. Why is this true? It's true because you can get everything in terms of sine and cosine. Why is this next line true? It's true because, well, you can get a common denominator in order to add fractions. So the verbal descriptions are important. It doesn't have to be formatted exactly like this, but the steps need to be explained adequately. Cool. So, these two results above are together referred to as Pythagorean identities. For, I guess, reasons that are reasonably obvious. they're all just the standard Pythagorean identity with some algebra around it. Cool. Any questions before we keep on going? All right. So, carrying on. So on this page, we see a single identity. Apparently, cosine alpha divided by 1 minus sine alpha is equal to 1 plus sine alpha all over cosine alpha. And we'll prove it two different ways, because I want to point out a shortcoming in the strategy that we've used for the previous couple, which is to start with the more complicated side and simplify it down. Does this equation really have a more complicated side? No, so it's hard to decide which one to start with. And especially if there's not one side that's more complicated, it's hard to see simplifications to do. And when you don't, well, maybe you can make a motivated choice of a complification, making one side more complicated in order to simplify it down in a different way. So let's try to prove this identity by picking a side and changing it to the other one. Which side should we start with? The left. Great. So let's start with the left-hand side and see what we can do to it. Cosine alpha divided by 1 minus sine alpha. And I don't really see any immediate simplification to make. Which is always a little upsetting. There's not an obvious step. Instead, I'll try to use this in order to motivate me. There's what I have. There's what I want it to become. So what's something you could do to just make this look more like that? Well, there's a 1 plus sine alpha in the numerator, right? So let's just multiply by 1 plus sine alpha. In order to do that, we also have to divide by 1 plus sine alpha. That's, I think, a not totally unmotivated choice of something to do. And when you're trying to prove something, you don't know in advance what the right steps are going to be. You're just trying stuff. Hopefully it'll work out correctly. So let's do that. Let's try multiplying by something to make the left side look more like the right side. So this will become cosine alpha times 1 plus sine alpha all over 1 minus sine alpha, 1 plus sine alpha, by multiplying and dividing by 1 plus sine alpha. So that's certainly a step that is not a wrong thing to do. You can always multiply and divide by a single number. It resolves the equality. So now that we've made that side more complicated, we want to go and simplify it down in a different way to get a different looking result. What's some stuff that you see that you can do here? Yeah.
Put foil
It's foil at the bottom. And conceivably one could distribute this cosine into the 1 plus sine alpha.
Yeah.
I think I want to not do that because having that 1 plus sine alpha there makes it look like I want it to look. So let's distribute the bottom. Let's leave the top alone. So this will become cosine alpha, 1 plus sine alpha, all over, and notice, foiling it out is going to be like a difference of squares situation. So let's use the difference of squares formula when we distribute. 1 minus sine squared alpha. So I'm not actually following this step by distributing. Anyway, there's more than one way to describe a task. I guess you said FOIL, so maybe I should also write FOIL. But the rule that's called FOIL is just the distributive law twice. Or maybe 3 times, depending on how you count. Nice. So we do that. What seems useful? I see something with a cosine squared or a sine squared. So let's, by Pythagorean, as long as I'm abbreviating proper names, I may as well be slightly legible. By the Pythagorean identity, what does that become when you use the Pythagorean identity? Yeah, it's just cosine squared alpha on the bottom. And if you're ever nervous, like, I'll be happy with Pythagorean identity, meaning any of the things that you can get out of Pythagorean identity plus a touch of algebra. All right, literally Pythagorean identity says cosine squared plus sine squared is always equal to 1. So this off to the side is scratch off, but I wouldn't, want to see in your actual write-up. But you can think this way. Sine squared is the same as 1 minus cosine squared. Oh no, 1 minus sine squared is equal to cosine squared. That's what I want. Which is nice because I see literally 1 minus sine squared, it'll become cosine squared. Great. So let's use that. By the Pythagorean identity, this becomes, ooh, it's a jazzy ringtone. Cosine alpha, 1 plus sine alpha, all over 1 minus sine alpha, 1 plus sine. God damn it, Chris. What are you doing? All right, cool. By the Pythagorean identity, we accomplished that. Anything cancel? A cosine. And nice. So that's like kind of exactly what I want. If I get rid of a cosine in the top and the bottom, I'll have the right-hand side of the equation. And so we're done. We've reduced the left-hand side to the right-hand side, so these two things are actually equal. So this strategy walked, but it had the downside of requiring like a starting step that you kind of needed to like, that wasn't totally motivated. There was a step that wasn't simplifying, it was making things more complicated. And if you see that step, then great, go for it. On the other hand, here's a second strategy you can use to prove an identity. You can do manipulations to both sides of the equal sign at the same time. So let's try to prove the same identity. Cosine alpha over 1 minus sine alpha equals 1 plus sine alpha all over cosine alpha. And we'll mess around with both sides of the equal sign. As long as we do the same thing on both sides, or do things that preserves equality, this will preserve equality. So if you want to see this whole equation and wanted to simplify, what seems reasonable? Well, if I asked you to like solve an equation that looked generally like this, what would you want to do for us? Say that right. Common denominator. That could work. I'll try something that we'll do a little bit more immediately to simplify, and that's equivalent to getting a common denominator, but then doing some canceling. Let's cross multiply. So cross multiplying says whenever you see fraction equals fraction, you can multiply the denominators onto the other sides. So let's cross multiply. That'll transform this equation into cosine times cosine, cosine squared alpha, equals 1 plus sine alpha, 1 minus sine alpha. Right, whenever you see a fraction equals a fraction, you can cross multiply. The common denominator idea would walk. I think it would just add an extra step. All right. So, what do you think with that starting step? You want to show these two things are equal. Well, I guess there's like stuff written, so it's kind of dishonest. But what seems like something reasonable to do next? Yeah, let's take the right-hand side. I don't like the word solve. Let's simplify it. let's write down what it's equal to in simple autons. And I guess that means distributing or boiling, depending on what one you like better for the situation. Oh, shoot, it's by the difference of squares formula you could write. So let's leave the left-hand side alone for now. Cosine squared alpha equals 1 minus sine squared alpha. All right, so here's the point. We've taken the original identity. We've done some algebra to it. We've reduced it to cosine squared equals 1 minus sine squared. If we can say why that is true, then we'll be done. Why is that? Well, yeah, why is that true? It is the Pythagorean identity. So I think I can even skip this next line. This final equation is true by the Pythagorean identity. So you've taken the equation you wanted to be true. You've done some algebra to both sides of the equation. You reduced it to something that you know is true. Whenever you can take an equation and reduce it by algebra to an equation you know to be true, you can conclude that the original equation was true. Since the Pythagorean identity is true, it follows that cosine divided by 1 minus sine is equal to 1 plus sine all over cosine. Groovy. Does that feel all right? Nice. So, I think what the next thing I want to do is here's an identity that I want you to prove. There's more than one way to prove this identity. I'd like you to take some time, come up with a proof of this identity. There's a suggested fourth step, but it's not the only fourth step you could possibly use. people are feeling done at this point? Oh, okay. Then I shouldn't come back together yet. That's not even close to a majority. Oh, maybe I should ask instead. Is anyone feeling stuck, like they'd like some guidance? Cool. Well, come on. Yeah, so distribute that out and do a bit of canceling and see what happens now. Okay, I'm going to try something. Sorry, wait.
Okay, that makes more sense.
Now do exactly what you wanted to do. So I think in the interest of just getting closure, well, yeah, let's come together and let's talk through the proof. So, what's the first step that people took? Let's express everything in terms of sine and cosine. Both sides of the equation or just one side? Just the left-hand side. So, there are two ways to do this, and this is one of the ways. So I'm going to try to fit this all on that half of the page. We'll see if it works. So the left-hand side, 1 plus tangent psi over 1 plus cotangent psi. What is that in terms of sine and cosine?
1 plus sine over cosine over 1 plus cosine over sine.
This is by expressing in terms of cosine and sine. Cool. All right. What next?
I think the one on top, I guess you would say, like cosine over sine, or cosine over cosine, and then the one on the bottom is sine over sine.
Nice. Sine psi over cosine psi should include the variables. You can always replace 1 with a thing that 1 is equal to. All right, what next? You got common denominator, so fractions can be added. So that'll become cosine psi plus sine psi all over cosine psi all over sine psi plus cosine psi all over sine psi by adding fractions. All right, what next? Yeah, so not just the cosines, like it's all of those that cancels, right?
Yeah.
Everything at the top is multiplied by the thing in orange, says everything in the bottom says those cancel. So you wind up with 1 over cosine divided by 1 over sine by canceling. All right, what next? Let's see, it looks like I see a fraction divided by, yeah.
So after you do the canceling, convert that into terms.
Yeah, I think that's going to be the goal. Maybe I'll add an intermediary. Yeah, I guess the intermediary is like, I see a fraction divided by a fraction. You divide fractions by multiplying by reciprocals. So that equals sine over cosine by dividing fractions. And finally, that equals tangent of psi as desired. So, how many people followed a strategy that seemed quite different from this strategy? Nice. That's why I left this space. There's one other obvious strategy. Hopefully there are only two general plans represented. So the other strategy, what was your first step? Yeah, I see a fraction on the left-hand side, so we can cross-multiply. And I guess we're just multiplying that side over to the other. So by cross-multiplying, this becomes, how am I doing for time? I have 2 minutes. 1 plus tangent psi equals tangent psi times parentheses 1 plus cotangent psi. Okay, what next?
Well, first I tried distributing, and then I didn't know what to do, so I crossed it out, and then I changed it to terms of sine and cosine, so I was kind of stuck at this point.
Cool. I'll distribute, and then let's rewrite in terms of sine and cosine.
Okay.
Because I think it doesn't matter what order you do these two things, but this order will minimize the number of symbols I need to write. So let's distribute this side, just like you said. 1 plus tangent psi, so by distributing, this becomes 1 plus tangent psi equals tangent psi plus tangent psi cotangent psi. And I know you said you gave up after this point, but what's do you see something that you could do here in addition to rewriting in terms of sine and cosine? Is there something in common on the left and right hand side? They both have a plus tangent. So I think I'm going to do two things in one step. I think I can subtract tangent from both sides. Because you can always subtract the thing from both sides of an equal sign if resolves equals. Let's subtract tangent psi from both sides. And express via sine and cosine. So I subtract tangent from the left-hand side, I just have 1 equals, subtract tangent, that piece goes away, this becomes sine psi over cosine psi times cosine psi over sine psi. Any ideas here?
Same thing.
Yeah, those two things are equal to each other. So let's just write a sentence saying why they're equal. These are equal by canceling. Groovy. Maybe as people are getting ready to leave, did anyone pursue a strategy that seemed different from both of those in a significant way? Okay, those two strategies were pretty representative of what people did? Nice. Did anyone write down an argument but leave out all of the words? Okay, yeah, when you write up something that you actually want another human being to see, like when you want to do your homework, make sure to include all of those. Because I know I harp a little bit on make sure to include some verbal descriptions in the open-endeds in general, but especially for this one. Especially since I'm already telling you what is equal to what. The verbal explanation as to why is what I really want to see.